Okay, Chem 1010 students, we're going to now move on with our introduction to organic chemistry. So now we're going to learn how to draw formulas for organic molecules. So we can draw full Lewis structures and show every carbon-hydrogen bond or every heteroatom carbon bond or every carbon-carbon bond. But there's many organic compounds which contain a lot of carbons. They're big organic molecules. So we want to find a way to represent that molecule, even if it's complicated. So there's actually shortcuts that we could take to designate these formulas or these organic compounds. So we're going to learn the different systems for writing the structures of organic molecules. And the first of these systems is called a condensed structure. So in a condensed structure, you do draw in all the atoms, but you omit the 2 electron bond lines and the lone pairs on the heteroatom. So for example, here's the Lewis structure of butane. Okay, so the ends of the molecule of butane contain a carbon bonded to 3 hydrogen atoms. So instead of writing the carbon with the three single bonds like this, we just denote that whole group as this carbon and the hydrogens attached to it. We just call it CH3. We give it a name CH3. It designates a carbon bonded to 3 hydrogens, and that becomes CH3. Now, if you have a carbon that's bonded to, say, 2 hydrogens, like here and here, the second and third carbon, we denote that CH2. And then what we do is we just go down the chain. We have CH3, the carbon bonded to 3 hydrogens. Then we write CH2, the carbon bonded to 2 hydrogens, the other carbon bonded to 2 hydrogens, and then we have another carbon bonded to 3 hydrogens. So this becomes a condensed formula. Now the carbon-carbon bonds are implied from these condensed structures. So the carbon-carbon bonds are between consecutive CH3 groups and CH2 groups, okay? And then of course, 2 CH2 groups next to each other, those 2 carbons are bonded. So this is called a condensed structure. So here's pentane, okay? It contains 5 carbon atoms and it contains 12 hydrogen atoms. So we can represent pentane as a Lewis type structure with the sticks, the single bonds drawn in as sticks for all the carbon-carbon and carbon-hydrogen bonds. We can draw a ball and stick model where the balls represent atoms, and they're color-coded by the atom type with carbon black, and of course the hydrogens are white. So we can denote the formula through a ball and stick model, but we can also write the condensed structure, CH3, CH2, 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 CH2. So there's 3 CH2 groups, and then there's CH3. And to even simplify things more, or to not simplify things, but to even write a faster way of the formula for this compound, we have something called a skeletal structure or a line angle formula. And in a skeletal structure, you draw the carbon, basically you draw carbon-carbon bonds only, okay? And they're drawn, in this case, as a kind of a zigzag pattern, because if remember each carbon in this compound is tetrahedral, so the carbon-carbon framework kind of forms a zigzag type pattern. So you draw the carbon-carbon bonds, and then you have to realize that at each end at the ends of the structure and at each vertex, there is a carbon atom. So there's 1, 2, 3, 4, 5 carbon atoms. So we draw pentane skeletal structure like this. Now notice we don't draw the hydrogens, but we can infer the number of hydrogens because remember that each carbon has to have four bonds. Now, this carbon here, for example, is bonded to this carbon here and this carbon here. So it already has 2 single bonds. So it needs 2 more single bonds. So to get those 2 more single bonds, you put single bonds in, you know that there's 2 hydrogens bonded to that carbon. So the hydrogens you can figure out the number of hydrogens from these skeletal structures. And then we're going to see more examples. You actually draw in, you do draw in the heteroatoms, okay? So now, some of the bond lines, if you have a branch in your organic molecule, you have a carbon branch. So here, if all the carbons were bonded one after another, then we would have a straight chain. But this second carbon, instead of bonding to a hydrogen, notice it's bonded to another carbon, okay? So this is called a branched alkane or a branched hydrocarbon, okay? So to draw the condensed structure for that, we leave one of the bonds for the branched carbon atom. Okay, so you have the CH3 group. You start with the CH3 group here. Then you have the second carbon. It's bonded to 1 hydrogen, and it's bonded to a branched CH3 group. And then, of course, it's bonded to the CH2 group here, which is finally bonded to another CH3 group at the end. So a carbon bonded to 1 hydrogen is denoted as CH. So you have carbon in these condensed formula, you have these, think of these units. You have CH3 units, which is carbon bonded to 3 hydrogens. You have CH2 units, which is a carbon bonded to 2 hydrogens. CH3 carbon bonded to 3, and a CH means a carbon bonded to 1, okay? So we can even go further and condense the condensed formulas even further. So for example, in butane, you have 2 of these identical CH2 groups that are bonded together down the chain. But so what you can do is put parentheses around a CH2 group and then put a subscript 2. And that means that you have 2 consecutive CH2 groups bonded together. Okay, you can play the same kind of strategy in this branch chain compound. You can actually, since there's 2 CH3 groups, you can start with this carbon atom, which contains a single H, CH, and then put the C. There's 2 of these CH3 groups bonded to this carbon, so you can put CH3 in parentheses and then 2. And then those 2 are bonded to this, since there's 2 groups, each of them is bonded to this carbon here. And then of course you go on to the CH2 and CH3 groups, the rest of the carbon atoms in this molecule. Okay, so here's some more examples of condensed structures. So you have a CH, this is 3 methyl, 3 methyl pentane. So this is the longest chain is 5. So you start with the CH3, CH3, CH2. Then you have this branch here. So you put the CH and then you put a bond to the branched chain, the branched carbon-carbon bond, CH3. Then you continue the chain, the longest chain with the CH2 and then the CH3. Okay, so that's that's an example of the condensed structure for this molecule. Now, when you have something with a double bond, again, start with the CH3, okay? Then that's the terminal carbon atom, the carbon atom at the ends of the molecule. Then you go to your carbon, that's the first carbon in this double bond. It's bonded to a hydrogen, so put CH. Then you put your double bond in, and then you put your other carbon, CH3. So notice you don't, in the organic compounds that just contain single bonds, you don't need to put a line connecting the consecutive carbons in the condensed structural formula. However, in double bonded hydrocarbons or double bonded or organic compounds that contain double bond, you do put in the double bond, okay? So here's an example of an alcohol. You have the hydroxyl group. So again, you have two of these CH3 groups. So I would start, this is where I would start, CH, and then you have the two CH3 groups in parentheses, and then superscript 2. Then you have your CH2 group, okay? But in addition, now you put in your hydroxyl group next to the carbon it's bonded to. So it becomes CH2OH. And you don't need to put the lone pairs in this condensed structural formula. But here's another example. So you have two chlorine atoms bonded to the first carbon. So what you would do is you can write the two chlorine atoms first, and you have two of them, so you put Cl subscript 2, then CH, CH2, CH2. Now there's two of these CH2 units, so you can condense it using the parentheses in the subscript 2. Then you have an oxygen bonded to this carbon, so you put in the O without the lone pairs, and then that's bonded to the next carbon, C. But notice now that this carbon is bonded to 3 CH3 groups. Okay, so there's no hydrogen. So what you can do is you can put the CH3 next to it in parentheses, and then subscript 3 to show you that there's 3 of these CH3 groups. Okay, so we're gonna convert each of these compounds into a condensed structure. So let's go for it. Okay, so to do this, you take the first one and just go down the chain. So you have CH3 first, there's a CH and a branch, so there's a line CH3. Then you have a CH2 group here. Then you have a carbon here with an H, and then you have two CH3 groups here. But you can condense this further because you have two identical CH3 groups here and two identical CH3 groups here. So what you can do is you can put the CH3 in parentheses and designate a 2, subscript 2, so that means there's two of these bonded to this red carbon here. And you have the same situation on the other end of the molecule. You have two of these CH3 groups bonded to this carbon in red on the right side of the molecule, on this side of the molecule. Okay, so that's the condensed structure for that. So for this condensed structure, well, you have CH3, CH2, CH2, then you have an oxygen without the lone pairs, then you would put CH2, Cl. Okay, but you can condense this further. You have two of these identical CH2 groups, so you put the CH2 in parentheses with a subscript 2, and then you further condensed the formula to basically as simple as you can get for a condensed structure. So let's do some examples of converting these compounds to some condensed structures. Okay, so let's write the condensed formula for the following Lewis structures. Okay, so for this molecule here, we start with CH3 here at the end. Then we go CH2, this carbon here, CH2, this third carbon here, CH2, this carbon here, and then CH3. So 1, 2, 3, 4, 5, 1, 2, 3. So this is the structure of pentane. They call it N-pentane. So what you can do to further condense it is realize that there's 3 identical CH2 groups. So we can put the 3 identical ones like that, and then we can write CH3 like this. So that would be the most proper condensed formula. Okay, for this one here, remember, we can write the bromine first, and then there's a CH2. We don't need the lone pair. Then there's CH2, and then there's a Br here. So we can write the formula like this. I think we can also write it. There's really 2 of these identical groups, so we might be able to write it like this, but I'm not absolutely certain. I guess we're safe writing it like this. Oh, actually, the other way you can probably do it is say Br, CH2, and then there's 2 of these, and then there's a Br. So this would probably be better to write it like this than this one. So I'm going to assume that this is not standard. So you can condense this further to this one here. So I'm going to leave that one up. Okay. Now this one here is an ether. So that's going to be CH3 here, CH2. And then that's bonded to the heteroatom O. Then you have CH2, and then you have a CH2, and then you have an OH, but you don't put the lone pair in. Now, the only way we can simplify this further is noticing that there's 2 of these CH2 groups. So what we can do is we can write this as CH3, CH2, O, and then there's 2 of these CH2 groups, and then OH. So we can draw it like that. Now the last one, there's a CH3. Here at the end, there's a CH2 here. Now, there's a carbon here, and that carbon is bonded to 3 CH3 groups, like this. So we don't really need to put a line in the main chain. So the proper way to do it would be like this. And then the branched methyls have these lines. However, there's 3 identical groups here. So you can condense this further to CH3, CH2, and then the carbon here. And then you have 3 of those CH3 groups, which are called methyl groups. Okay, so those are some examples. Okay, so now we're going to go the opposite direction. We're given the condensed formulas, and then let's write the full Lewis structure. So if we start here, there's a CH3 group. So we're going to do it like this. And then there's 8 of these CH2 groups. So 1, 2, 3. This is tedious. 1, 2, 3, 4, 5, 6, 7, and then 8 finally.
All right, so we have that, and then we have CH, another C, and then H, CH3. So this is really C10, H22 if you count everything up. So this is a structure of N-decane, so it's a pretty big for a medium-sized hydrocarbon, not extravagantly big, but okay, so this one here, so that would be CH3. No, we're not repeating the condensed formula. Usually you go, so you get CH3 like this, and then two of these, four of these, 1, 2, 3, you get 4, 1, 2, 1, 2, 3, and then one more, and then one more, and then you have a hydroxyl group. So this is an alcohol. This is pentanol. It has 5 carbons, so the name for this is pentanol. Pentanol, or N-pentanol, and then this is N-decane. We're not going to get too much into nomenclature in this course. In a full-fledged OChem course, you would have to do that. This one here, see, this is a little easier. So this one would be CH3, C, Cl, Cl, Cl. Oh, we got to draw in the lone pairs. So if we draw in all the lone pairs here, this is like the chlorine. Okay, so so that's that compound. Then if we draw this one here, C, H, 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 C. There's 4 of these, so we gotta write 4 again. So we have 1, 2, 3, 4, and then we have C, H, and then we have 2 CH3 groups. Well, let's redraw it. If we draw all the C, okay, so like that. And then this one down here, we have C, then you have an H, and then you have 2 of these methyl groups, CH3 groups, and then C, H, 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 so you have 2 of those, CH, then you have a CH2 group, and finally you have a nitrogen, and then there's 2 hydrogens there, and then there's a lone pair on those nitrogens. So that's the going from the condensed to the Lewis structure with the lone pairs on the heteroatoms. Okay, so now we're going to talk about these skeletal structures or line angles. Okay, so in these skeletal structures, you assume that there's a carbon atom at the junction of the 2 lines or at the end of the lines, and then you can infer the number of hydrogens by just knowing that each carbon must have 4 bonds, and then we draw in the heteroatoms and the hydrogens that are bonded to the heteroatoms. We don't need to draw the hydrogens for the carbon-hydrogen bonds in the skeletal structure, but we do put hydrogens bonded to these heteroatoms. So here's an example of cyclohexane. So cyclohexane, the Lewis structure is shown like this, where you have a carbon bonded into a ring, a hexagonal ring type structure, and each carbon then has to have 2 carbon-hydrogen single bonds. So this is a cycloalkane structure. To make a condensed structure, all you do is you draw a hexagon here, the skeletal structure, and then at the vertex of the hexagon are carbon atoms. And notice we don't need to add the hydrogens in these condensed structure. It's inferred because, for example, this carbon here contains is bonded to another carb. This is bonded to two other carbons. So you need 4 total bonds. So you need 2 carbon-hydrogen bonds. So you know that you're going to have 2 hydrogen bonds, 2 carbon-hydrogen bonds, or 2 hydrogen atoms bonded to this carbon. In fact, you're going to have 2 hydrogen atoms bonded to each of the 6 carbons in this cyclohexane structure. Here's another example. Here's the Lewis structure for cyclopentanol, which is it's a cyclic alcohol. So again, you draw the framework, the carbon framework, which would be a pentagon. And remember, we draw in the heteroatom and the bonds to the heteroatom. So we draw in a single bond to the oxygen. And then we also put in the hydrogens that are attached to the heteroatom. So we put in, we don't need to put a line to denote the bond. We just put a hydrogen next to the heteroatom, and that indicates that it's bonded. So there's the skeletal structure for that. So we're going to, again, we're going to do some examples here. We're going to convert each skeletal structure to a complete structure with the carbons, hydrogens added in, and the lone pairs added in on all the electrons. So we're going to do that on the whiteboard. Okay, so we're going to draw the Lewis structure. So for the first one here, so we're going to draw, we have an 8-membered ring. This is cyclooctane, so we have 8 carbons bonded together in an octagon, something like this. But then we know that we have to have 2 hydrogens because there's 2 bonds here, and we have to have 4 around each carbon. So we have 2 here, and then we have 2 here, and then we have 2 here, and then of course we have 2 here, and then we have 2 hydrogens. Sorry. So we have, so this is the Lewis structure with all the atoms explicitly drawn in, and this is cyclooctane. I think we just need to eliminate one of the O's. So this is cyclooctane. I think it's like that. So this one here, we would have a 6-membered cyclohexane. Now, what am I doing? We want to draw the carbons explicitly. So this one would be, C. Let's put in the ring, C, 6 carbons arranged in a hexagon. Then like this. Now there's a chlorine on this one, but there has to be another hydrogen because you need 2 bonds. Notice you only have 1 hydrogen and not 2 here because the carbon chlorine already takes up one of the bonds, and then you'd have something similar, the same arrangement. And then I'm not going to draw all the lone pairs for each chlorine. There's 3 lone pairs, so you draw 3 lone pairs about each chlorine. What the hell? I'll do it. Okay, and then 1, 2, 3, 4, 5, 6. So there's the Lewis structure of this this compound here, and then this is also a cyclohexane type of molecule. So we're going to draw it like that. Then we're going to, there's 1 bond to the hydroxyl group. So we're going to put the lone pair in, and then the next one also, you need a hydrogen, and then you need this carbon-nitrogen bond, and then this carbon here would have 2 hydrogens, and then this carbon here, 2. This one here, you have a methyl group, like that. But then you have to have another hydrogen, so you have 4 bonds to that carbon, and then also you have it like that. So there's some examples for converting skeletal structures to Lewis structures. Okay, so we did it both ways. Okay, now we're going to draw skeletal structures for long carbon chains. We learned how to do it for cyclic compounds. So again, this compound here is hexane. What you do is you put the lines, you draw a series of zigzag lines, and you arrange draw it so that there's a carbon atom at each terminus of the ends of each line, and then there's a carbon atom at the vertex. So there's 1, 2, 3, 4, 5. There's 6. There's 6 of these. There's 6 carbon atoms denoted by this skeletal structure. And then of course here's the ball and stick model. Okay, so zigzag is the key. All right. So here's an example for how to interpret a skeletal formula. So if you were given this skeletal formula, what you do is you place a carbon atom at the intersection of the 2 lines, and then you also place a carbon atom at the end. So what we can do first is we can put a carbon atom, we can follow this rule, put carbon atom at the end, and then a carbon atom at the intersection of 2 lines. Okay, and then of course we kept the carbon-carbon double bond, the carbonyl, the C double bond O group, and the COH group. Okay, so now what you want to do is you want to now add hydrogens so that you make each carbon tetravalent, or you want to add hydrogens. In other words, you want to add hydrogens so that you have 4 bonds, and you want an octet, the carbon to have an octet of electrons. So you bond it with enough hydrogen to achieve, for that carbon to achieve an octet. So for this carbon here, of course, you have 1 carbon-carbon double bond. You need 3 more, so you put in 3 hydrogens. The carbonyl group, you have a carbon-oxygen double bond with 4 electrons, and then you have 2 bonded electrons. So you don't need to put any hydrogens in this, the carbon in the C double bond O. The oxygen itself you don't need to add hydrogens. Again, if it was a heteroatom, then you would put in hydrogens explicitly. Okay. Now, for this carbon here, you already have 4 electrons in this double bond, and you have 2 more here in this single bond, so you have 6 right now. You need 2 more to make the octet of electrons on this carbon, so you need to add a carbon-hydrogen double bond. And this carbon here, you need to add a carbon-hydrogen single bond. Did I say double bond? Carbon-hydrogen single bond on each of these carbons here. So now you have a carbon with 2 single bonds, so you need 2 more hydrogens, bonds with 2 more hydrogens, 2 more carbon-hydrogen bonds. So you bond with 2 hydrogens here. Now this carbon here, it already contains 2 single bonds. One of the single bonds to another carbon, the other is to a hydroxyl group. So to make the carbon tetravalent, you need 2 more bonds. So then you would put 2 hydrogens here. Okay, and then the final step is to add your lone pairs to the heteroatoms. Okay, So let's again do what we're going to do is we're going to convert skeletal structures to complete structures with carbons and hydrogens drawn, and we're going to add the lone pairs to the heteroatom. Okay, so let's draw some line angle formulas here. So if we draw this formula here, the first thing we can do is we can put in the carbon atoms at the ends and at the vertex. Okay, so now we've got the carbons, and we have 1, 2, 3, 4, 5, 6. 1, 2. Well, actually, there's a carbon here. So 1, 2, 3, 4, 5, 6 carbons. Now we can add the hydrogens like this. I'm just going to abbreviate it like the condensed form. There's going to be a hydrogen here, and then there's going to be 2 hydrogens here, and then there's 2 hydrogens. What's wrong with this? And then there's 2 here, and then there's 3 here. So if we were going to write the condensed formula for this, it would be CH3, CH, CH3, CH2, 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 CH3, but we can condense that further to CH3, 2, CH, CH2, and then there's 3 of these, so we can do this, and then we can say CH3 like that. So we can draw it like that. Okay. Now, if we do, say, this one here, cyclooctane, or this is like a cyclohexane type of derivative. Then there would be a carbon, 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 oxygen, carbon, carbon. All right, and then there's a carbon here, and then there's a hydroxyl group here. So what we can do is we can put CH2 here. There's 2 hydrogens. I'll put it like this. And then there's a hydrogen. There has to be a hydrogen bonded to this carbon because there should be 4 bonds. There's 2 lone pairs on the oxygen. And then there's 2 groups attached to this oxygen. Of course, there's going to be 2 hydrogens here, and then your OH. So that's the condensed formula for that molecule. Okay, and then the last example, we have, say, Br. So to do this one, we would put C, and then we put C here, and then there's a C here, and then we leave a double bond here, and there's a C here, and then there's a C here, C here, and then there's a C here, and then there's a Br. So what we can do is we know this is a methyl group here, and then this is also a methyl group, 3 hydrogens. This one only needs, you don't need to add a hydrogen to this carbon because it already has 4 bonded groups, a double bond and 2 single bonds. This one here, we need to add 1 hydrogen here because there's 1, 2, 3, 4, 5, 6, 7, 8. So you have 4 in this double bond. Oh, I don't know why this is doing this. Sorry, this is frustrating. So I'm just gonna redraw this I'm just going to do it quickly. CH3, like this, CH3, and then you have the double bond, CH, CH2, 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 and then you have the bromine here. So the condensed formula then would be, why is this doing this? You'd have C here. So you'd have C, double bond, CH, then you have CH3, 2, CH, then you have CH2 twice, and then you have CH2Br. So that would be the condensed formula for that. And we're not, if we drew in the lone pairs, of course, there would be 3 lone pairs on this bromine. Okay, so now what we're going to do is we're going to use the skeletal structure to determine the molecular formula Stig-Lipton, a drug used to treat type 2 diabetes. So let's redraw the formula on the whiteboard. Okay. So the structure of Stig-Lipton is like this. Then we have like this, and then we have NH2, and then we have like this, and then we have a carbonyl group, and then we have a nitrogen here, and then we have a nitrogen like this, and then we have, we go something like this, okay, and then we have a double bond here, nitrogen, we have another double bond here, then we have like a 5-membered ring, sorry, that, and then we have CF3. So how many carbons do we have? We have 1, 2, 3, 4, 5, 6 carbons here, 7, 8, 9, 10, 11, 12, 13, and then we have 14, a carbon here, and then we have 15, so C15. Now what about the hydrogens? Well, we have to add the hydrogens. Why is this doing this? So we have a hydrogen here, okay, because we have 1 bond here, a double bond here, so we need 1 more hydrogen carbon single bond. We have a hydrogen there. We're going to have 2 hydrogens here, okay, and we have 2 here, and we're going to have 2 here, and then we're going to have 2 here, and then we're going to have 2 here, and we have 2 here. Okay. And what do we have on the nitrogens? So we draw on the lone pairs here. Let's just draw in for completeness sake. Okay, so then now the nitrogens, we don't need any hydrogens on this nitrogen. So 1, 2, 3, 4, 5, 6. So this nitrogen also has a lone pair. This nitrogen here would have a lone pair. And we don't need a hydrogen on this carbon because it's already involved in a double bond. So how many hydrogens does that give us? 1, 2, 3, 4. 4 plus 2 is 6, 7, 8, 9, 10, 11, 12, 13, 14. So I count, gosh, H, sorry about that. I don't, so C15, H14. Okay, so hydrogens, then how many, I don't know why this is doing this. Okay, this is not good. This doesn't seem to be working. I don't know why. Okay, so we're back again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 carbons. I think I miscounted in the last one, or did I? Let's see. So we have the nitrogen here. Okay, let me do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Why do I get 14 now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's a carbon here. 13, 14, 15. So yeah, C16 hydrogens, H 1, 2, 3, 4, 5, 6, 2 here, 8, 9, 10, 11, 12, 13, 14. So 14 hydrogens. How many nitrogens? 1 nitrogen, 2, 3, 4, 5. So I count 5 nitrogens and 5. How many oxygens? I see 1 oxygen. And how many fluorines? Well, there's 3, 4, 5, 6. So I get F6. So this would be the molecular structure or the molecular formula for Stigpelin. So the trick here was to first identify the carbons, what the carbons were. The heteroatoms are already there explicitly. Identify the carbons and then put in the hydrogens, figure out how many hydrogens are bonded to each carbon. Okay, so now we're going to talk about the concept of functional groups in organic compounds. So we talked about how organic compounds are composed mainly of carbon and oxygen, but it also contains it can contain other types of atoms, oxygens, nitrogens, sulfurs, in some cases carbon-oxygen carbon-oxygen groups. And these groups that are covalently bonded to the framework, the main carbon-hydrogen framework of the molecule or the organic molecule, these groups are called functional groups. In some cases, the functional group can be a single atom. In another case, it can be groups of atoms. But the thing about the functional groups is the functional group that an organic molecule contains, that's used to classify the type of organic molecule. It also is a benchmark for characterizing the chemical and physical properties of that organic molecule. So functional groups are kind of a way of indexing the different types of organic molecules. And they're also sometimes called functional groups. So we're going to go over the common types of functional groups in organic compounds. But first, a functional group, remember we can say that it contains a heteroatom, usually a group of heteroatoms with other types of atoms. It could also be in a compounds containing carbon hydrogen, just a carbon hydrogen double bond, or a triple bond, or multiple carbon hydrogen, multiple carbon bonds, or it contains sometimes both multiple bonds and heteroatoms. So the way that we designate a functional group, or we specify, abbreviate or specify a class of organic compounds with a functional group, is with this symbol R, where R denotes the carbon backbone of that molecule, and then we have a single line, and then we put the formula for the specific functional group that's contained in that particular organic molecule, and we'll go over some of these functional groups soon. Now, again, the letter R is used to abbreviate mainly the carbon and hydrogen portion of the molecule. Okay, so here's an example of an organic molecule with a functional group. So the functional group here is a hydroxyl group. We've encountered this before, and this groups of organic molecules that contain this functional group are called alcohols. Here's an example of ethanol. So the the backbone, or the R group in this case, is this portion of the molecule, the carbon hydrogen or carbon backbone. And then you have the hydroxyl group. And then of course, this is the space filling representation. Okay, so let's talk about, we do have classes of organic compounds that contain only carbon hydrogen bonds. Those are called hydrocarbons. So we're going to go over the different classes of hydrocarbons. So first of all, the alkanes. Alkanes are a class of hydrocarbons that only contain carbon-carbon single bonds and no other functional group. Alkenes, on the other hand, they have a carbon-carbon double bond as their functional group. Alkynes have carbon-carbon triple bonds as their functional group. And then there's a class of hydrocarbons called aromatic hydrocarbons. And those contain a benzene, or a six-membered ring with alternate double bonds, and three double bonds to be specific. And these types of compounds that contain benzene rings, these are called aromatic hydrocarbons. So these are considered the functional groups, or more specifically, the classifications of hydrocarbons. Okay, so here's an example how we denote the functional groups of a hydrocarbon in specific examples. So if you just have a carbon-carbon bond in alkanes, you can abbreviate it like this, RH. And here's an example of this is an example of a molecule of ethane, and then of course you have the 3D structure. So the alkane itself is the functional group. Now, if you have an alkene, you have a carbon-carbon double bond, and an example would be ethene or ethylene. And the functional group there itself is this carbon-carbon double bond. The alkyne contains a carbon-carbon triple bond, and this is the general structure. And you have an example here of acetylene or ethine, and the functional group again is the carbon-carbon triple bond. This is the aromatic group I was talking about, the benzene. This is the benzene ring itself, or this is a structure of a molecule, a line angle structure of the molecule of benzene. So it contains a six-membered ring with alternating carbon-carbon double bonds. So it's the functional group there is for example, benzene. Okay, so here's an example of an alkane, a long alkane called polyethylene, and polyethylenes they they are parts of the plastic chains. And alkanes are, since they don't have functional groups, or they're not considered to have functional groups, they're the basic carbon skeleton in organic compounds. They're pretty much unreactive, with some exceptions. You can have free radical alkylation of alkanes, but you can also have a combustion, which is a very important class of reactions. But for the most part, they're pretty inert. So polyethylene, these long carbon chains in nature, can be very unreactive, and it's very difficult for these long chain alkanes to break down. Okay, so now if we do have functional groups that contain other types of atoms that usually contain single bonds to the carbon hydrogen backbone, which again we designate as R here. So the first class of compound is the alkyl halide compounds, and the functional group there is a halogen or a halo group. So here the general structure is R, and then you have a single bond with the halogen atom X, and the lone pairs are drawn in here. So example of an X or a halogen atom, a heteroatom, could be fluoride, fluorine, chlorine, bromine, or iodine. Here's an example, methyl bromide. Okay, so this is considered, these are called alkyl halides. Okay, so here's a ball and stick representation of this methyl bromide molecule. Of course, you can have methyl fluoride, methyl iodide, etc. The second class of organic compounds, another class of organic compounds with this OH hydroxyl functional group, we talked about this already, are the alcohols. So an example for those types, that class of molecule would be methanol here. So you have a single bond between the carbon and the oxygen, and then you have the two lone pairs on the oxygen. An additional class of organic compounds, but instead of containing one carbon, the hetero group is an oxygen atom, but instead of containing one bond to a carbon and a bond to the hydrogen, you replace the hydrogen by another alkyl group. And it doesn't have to be the same alkyl group, but it can be the same. And you denote that by R bond O bond R, where R is, you have two alkyl groups. So in this case, the alkyl groups, in this example, the alkyl groups are both the same on both sides of the oxygen. And so this is an example of this is called dimethyl ether. These class of compounds are called ether. And the group, here we call it a hydroxyl. So we call this group here, OR, an alkoxy group, alkoxy group. Okay, so ethers contain as the functional group alkoxy groups, and there's really two of them, one on each side of the oxygen bond. Now we get to, so these two classes of organic compounds contain single bonds to the alkyl groups. Okay, there's some other types of functional groups that contain single bonds to the R group or the hydrocarbon framework, and the ones that contain nitrogen are called amines. So you have a single bond between an R group and a nitrogen containing group. The nitrogen containing group can be NH2, or you can have two R groups bonded directly to the methane and a hydrogen. These are secondary amines, these are primary amines, and then if you have three R groups instead of the three hydrogens attached to the carbon-nitrogen bond, then you have a tertiary amine. So an example of a primary amine where you have just two hydrogens, and you have two hydrogens, two separate nitrogen-hydrogen single bonds and an additional carbon nitrogen bond in these RNH2 compounds or these primary amines. An example would be methylamine. And remember, the reason you can have up to 3 is because if you have three groups surrounding, or 3 bonds involving this nitrogen. So nitrogen in compounds can have 3 groups. So you can have one carbon-nitrogen bond and 2 nitrogen-hydrogen bonds, single bonds for 3 groups. And then you have the lone pair. Or instead of like 2 hydrogens, you can put 2 separate R groups, or two carbon-nitrogen single bonds and 1 carbon-hydrogen single bond, and that's called a secondary amine. And a tertiary amine, instead of hydrogens, you have 3 carbon-nitrogen bonds. Okay, so this is these are the amines, and the group is called the amino group. And finally, there's where you can have a sulfur instead attached, bonded to the carbon in the R group or the backbone, and that's called a thiol group, and the name of the functional group is called a sulfhydryl group. So an example of that type of group would be methyl sulfide, okay, or yeah, methyl sulfide, right? So here's some examples of a functional group containing a single bond to the heteroatom. So in this case, we can have an ether where you have oxygen with 2 lone pairs that are bonded to 2 R groups, or 2 carbon-hydrogen frameworks. So this is diethyl ether, the condensed formula for diethyl ether. So oxygen is bonded to a carbon on this side, and then the carbon on this side, and then of course you have the 2 lone pairs. Another example of a more complicated example is tetrahydrocannabinol, which is THC. And in THC, you also have an ether group because you have an oxygen bonded to 1 carbon on one side, and then a separate oxygen carbon bond over here. So this is so you have an ether group in this THC, even though it's a cyclic type of a molecule. So here we're going to just quickly identify some functional groups. Here's 2-propanol, or also called isopropyl alcohol. And in isopropyl alcohol, we have a hydroxyl group, an OH group, which is the functional group, and that's bonded to the middle carbon here. And so the functional group is the hydroxyl group, and this belongs to a class of organic compounds called molecules. Now, styrene is the starting point for making styrofoam. And styrene actually contains 2 functional groups. It contains this carbon-carbon double bond. So so styrene is an alkene, considered an alkene. Those carbon-hydrogen, those hydrocarbons that contain 1 or more carbon double bonds. But then it's got this benzene ring. Okay, so it's aromatic too. It's got an aromatic functional group. And then last example here is a compound called putrescine. And putrescine, it contains these 2 amino groups, okay? So this putrescine belongs to the class of organic compounds known as amines, okay? So let's do some more examples here. Geraniol is the main component of rose oil. So again, we said that this compounds, we saw some examples where they contain more than 1 functional group. So geraniol, it contains 2 carbon-carbon double bonds. So it contains one of the functional groups, the carbon-carbon double bond, as in alkenes, but then it also contains a carbon-oxygen single bond in a hydroxyl group, which makes it an alcohol. Okay, these class of natural products, plant products, are called terpenes. Okay, so this is an example of a terpene. And they contain these like branch chain units here called isoprenoid units. Right, so this molecule here, sevoflurane, which is used as an anesthetic, this actually contains an alkyl, several fluorine molecules, several halogen, carbon halogen bonds. So this is an alkyl halide. And there's an alkyl halide, a halide group here, an alkyl and a halide group here, a halogen group here. But in addition, it contains an oxygen with two separate carbon oxygen single bonds. So this is characteristic of an ether. And this one here, this example here, it contains a nitrogen. A nitrogen also usually contains three bonds plus the lone pair. And these three bonds are carbon nitrogen bonds. So this is a tertiary amine, and this is the amino group in this triethyl amine. Okay. Now we talked about carbon single bonds between heteroatoms and carbons. We can also have functional groups that involve multiple bonds between the carbon and the heteroatom. And in this, the most common functional group where you have a double bond between the carbon atom in the R group or in the main skeletal structure are called carbonyl groups. So these carbonyl groups are present in several different types of compounds. And remember, just going back, according to Vespar, this is a trigonal, a planar geometry about the carbon with bond angles of 120 degrees. There's two lone pairs about the oxygen to make an octet of electrons on the oxygen atom. And in contrast to alcohols, where there's a hydrogen attached to, covalently bonded to the oxygen, this oxygen now does not contain oxygen hydrogen single bonds. It only forms a double bond with the carbon. So here's a table showing the different types of compounds, organic compounds that contain carbon oxygen functional groups. So the first example is an aldehyde. In an aldehyde, you have a general structure where you have the functional group is this portion here, where you have a carbon group. We call this the carbonyl carbon. This is the whole carbonyl group. There's one single bond to this carbonyl group, atom of the carbonyl functional group to the R group. Okay. And then there's another single bond to a hydrogen. So here's an example, acetaldehyde here would be an example of an aldehyde. And of course you have the 3D ball and stick structure. So if you have a carbon oxygen double bond, and in that carbon, there's a bond to a hydrogen, a single bond to a hydrogen, and another single bond to the rest of the molecule, or the R group, we call it. Then this is an aldehyde, a related class of compound. This class of compound is called a ketone. Now, instead of having a hydrogen here, you have two R groups. Okay, so you have instead of having a carbon hydrogen bond and a carbon carbon bond to the carbonyl carbon, you have two carbonyl carbon bonds, or the bonds to two R groups. And this would be how you would denote this functional group, where there's a carbon in the carbonyl group, of course, and then there's another carbon bound to another carbon atom of some skeletal structure here, and another carbon atom to either a separate skeletal structure or the same skeletal structure. Like in this example, this is acetone, where you have the carbonyl carbon, a bond to the carbon of another R group on both sides of the carbonyl carbon group. So this is acetone. Now, if you take the carbonyl oxygen, and then you bond that now to an hydroxyl group, an OH group. You have a new group. You know, it does not have, it has completely different properties. Don't think by just adding an OH group, you're going to get the same properties of an alcohol. No, you don't. You get a completely new class of organic molecules called carboxylic acids. And the carboxylic acids have this portion as the functional group, and then this, through the carbon atom of this functional group, the carboxyl functional group, you form a single bond to the rest of the rest of the molecule, or the R group. So in this case, this molecule here, you have an example. You have what's called acetic acid, which is basically the main component of vinegar. So here's a carboxylic acid. And now it's just in changing these functional groups involving the CO group, you leave the carbon bond between carbon in the carbonyl group and the carbon in the skeleton structure, and then you replace the hydrogen with another R group in ketones, an OH group in carboxylic acids. But now if you replace it with an oxygen bonded to another R group here, then you have what's called an ester. Okay, so this is the functional group of the ester. And the nice thing about esters is that they're usually very pleasant, smell very pleasant, and they usually give, like fruits, a lot of the fruits, their aroma. So an example of this would be an example of an ester compound. I think this is dimethyl ester. This is dimethyl ester, where you have two. The methyl group, or the CH3 group, is the R here, and then the R here. And then lastly, if you put an amino group, you bond a carbon-nitrogen bond to the carbonyl carbon, then you have a class of compounds called amides. So the designation for the functional group of the amides is here. You don't necessarily have to have hydrogens here. You can put carbon-nitrogen bonds instead of carbon-carbon bonds, or you can have just in this case, you have a primary amino group. So you have functional groups within functional groups, like these compounds here. You can think of them that way. But these are the the classes of organic molecules that contain a functional group involving the C double bond O group. All right, so here's an example of some molecules containing carbonyl type functional groups. So here's the aldehyde group here. So we call this an acid aldehyde, and here's an example. So an aldehyde, the hydrogen atom is directly bonded to the carbonyl carbon, and so here's an example of acid aldehyde. And then a ketone, instead of having the hydrogen bound, you have two R groups, and they don't need to be the same R group, okay? And so a ketone has two alkyl groups bonded to the carbonyl group, all right? And so the two alkyl groups in this case are two CH3 groups, and so this is an example of acetone, and we can draw the condensed formula for acetone like this, where you have a carbon, and it's singly bonded to two carbons, and then the carbon here is doubly bound to the oxygen. And then acetic acid here, you have when the condensed structural formula, you can draw it as CH3COOH. Sometimes you write it as CH3CO2H. And in the carboxylic acid, the OH group is bonded directly to the carbonyl oxygen. The esters, an ester contains an OR group directly bonded to the carbonyl carbon. So in this case, the OR group is here, where I'm circling. And here's some condensed structures for an ester type of group. Okay, so, all right, so again, we said that these carbonyl groups, a lot of them are associated with natural products. So benzaldehyde is associated with the aroma of cherries, isoamyl acetate, which is an ester, that's associated with the flavor or odor of bananas. Citric acid in citrus has many of these carboxyl groups, and ethyl butanoate is an ester, and it's responsible for the pleasant odor of bananas. Okay, so cherries and almonds are actually aldehydes, benzaldehyde. So those are some of the common flavors and smells associated with some of these carbonyl functional groups. So we're going to do some identification of functional groups. This, of course, is a carbon-carbon double bond here, so an alkene. This is a hydroxyl group off the 6-membered ring. Here you have a carbonyl functional group, the carbonyl carbon, and it's bonded to one carbon here and a second carbon here. So this is a ketone. Even though it's in a cyclic backbone, it's still considered a ketone because the carbonyl oxygen is bonded to two carbons, okay? This one here, this is going to be, even though it has an aldehyde group here, because you have a carbon that's bonded to a hydrogen, which bonded to the carbonyl oxygen. This is a carboxylic acid, okay, because you have carbonyl oxygen and then you have an OH group. Another ketone here, all right? This one, I think this is going to be Br. So this one where you have the CO2 group in the middle, that's going to be an ester, and then this one here is going to be this one's going to be an amine. So let's do this a little more carefully. Okay, so I want to show some more examples of some functional groups here. So this molecule here, if we draw out the functional group, this is the condensed formula. So here we'd have a COH here, and this would be an example of an aldehyde. Okay, so here's an example of an aldehyde. Now this compound here will condense it even more. So you have CO2H, so that would denote a COOH, and if you have an OH group here, this is the functional group, and this is a carboxylic acid. This group here, we don't have to abbreviate further. This is a ketone, okay, because it contains, you have the carbon bonded to two additional R groups here. So this whole group can be considered a ketone. This one here, CH3, CH2, C, now we have an O, double bond O, it has to have a carbonyl. So the other oxygen is here. And then you have CH2, CH3. And then if you put the lone pairs here, by the way, if we put the lone pairs here, for completeness sake, we'll have it like this. And then we'll have lone pairs here. So this is an ester. And then here we're not going to really specify it further. All I'm going to show you, well, we will specify it further. So if you have something like this, you can have, this is an amine group. More specifically, this is a secondary amine. Okay, because in a secondary amine, you have two carbon nitrogen bonds, two bonds carbon nitrogen bonds, or two bonds to the involved, two carbon nitrogen bonds in the functional group. If you had a third here, it would be a tertiary amine. And if you had none, these were both hydrogens, it would be a primary amine. Okay, so let's do an example, a little bit more complicated organic compounds. We're going to do two examples. One of them is a drug, an antiviral drug called Tamiflu, which is used to treat influenza. And here's the condensed structural formula for Tamiflu. And then the other example we have is atenolol, an hypertensive agent used to treat high blood pressure. So if we identify the functional groups in this molecule, so here we have an oxygen with two carbon oxygen bonds from the functional group. This would be an ether. Here we have a CO2 group. So one of the oxygens is in a carbonyl group, and then the second oxygen is a carbon oxygen carbon single bond. So this is an ester here. This is an amine group here. And this group here, actually, this here is an amide group where you have the nitrogen is actually bonded to one carbon and one hydrogen, and then you have a third nitrogen carbon bond here. So this specifically would be a secondary amine. Okay, so now this compound here, atenolol, you have an amide group here, a carbonyl oxygen nitrogen group. You have a benzene ring here, or an aromatic group. You have an ether oxygen here, an oxygen carbon on the site. Here you have a hydroxyl group, similar to an alcohol. And then here I see a nitrogen, which is bonded to a hydrogen and two other carbons. So this group here is an amine group. Okay, so there's the functional group here's examples of identifying functional groups in two different pharmaceutical compounds. Okay, so some of this here might be review, but we're going to go over some of the properties of organic compounds. And some of those properties are that organic compounds, generally they're composed, only of covalent bonds. And organic compounds, remember, there's three different types of intermolecular forces. There's London dispersion forces, which are the weakest of the forces involving temporary dipoles. There's the hydrogen bonds, and then of course there's London dispersion forces, which involve temporary dipoles. In molecules, there's ion dipoles, and then there's hydrogen bonds. And it's usually these weakest London dispersion forces that play a significant role in intermolecular interactions in organic compounds. In some of the classes of organic molecules with heteroatoms, you have hydrogen bonding as an important intermolecular force. And as a result of these weaker London dispersion forces in some of the organic compounds, they have lower melting and boiling points. And a lot of the organic compounds tend to be because they have these weaker intermolecular forces, they tend to be liquids and gases at room temperature. And in contrast, ionic compounds are more solid. And remember that if you have a carbon-carbon-hardrogen bond, you have a very small electronegativity difference between the two atoms. So you have what's considered a nonpolar bond. However, if you have a carbon-oxygen bond or a carbon-nitrogen bond or a carbon-halogen bond in these heteroatoms, you have a net difference in significant difference in the electronegativities between the two atoms in the bond. So this bond has a more polar character with the electron distribution towards the more electronegative element. So the dipole moment in the carbonyl type compounds points towards the oxygen, and you get a partial positive charge on the carbon, partial negative charge on the oxygen. Here, the partial negative charge on the nitrogen compound, the electron distribution is pointed more towards the nitrogen, and in here, halogens are the most electronegative, so the carbon halogen bond is even more polar than the carbon nitrogen and the carbon oxygen bond. So, so here's an example where ethane, the molecule is nonpolar because there's no polar bonds. Remember, the overall polarity of the entire molecule is really dependent on the bond polarities of the individual bonds in the molecule and the overall shape of the molecule. Now, so ethane does not have a net dipole, but chloroethane now does, because you have one polar bond. So that sort of pulls the electrons in one direction, at least among this bond, and gives the overall molecule a net polarity. Now, some molecules, here's an example, dichloroacetylene. You do have individual bond dipoles, and the bond is this bond here is polar, and then this bond here is polar. But the two dipoles, the molecule's linear, and the dipoles are oriented in opposite directions, so you get a net cancellation. All right, and in other types of molecules like ethanol, for example, you do have a net dipole pointed to the oxygen from the carbon-oxygen bond, and also you have a net dipole in the hydrogen-oxygen bond. The two dipoles do not cancel, and the molecule does form a net dipole. So the overall molecule itself, methanol, is polar. And remember, polar compounds that involve bonding a hydrogen attached to an oxygen, a nitrogen, or a fluorine. Those can form hydrogen bonds with other methanol molecules, or it can form hydrogen bonds with solvent molecules such as water. Okay, so we're going to use this. We're going to use shape and bond dipole to predict why some organic compounds are polar. So we want to explain why methylene CH2Cl2 is a polar molecule. Well, we know the overall shape of the molecule is going to be tetrahedral, and we know that chloride is electronegative, and that the carbon chloride bond, the carbon chlorine bond, has a net polarity to it. So you have an overall net dipole moment. Now, if it was carbon tetrachloride, four of them, the individual, the four bond polarities, individual bond polarities would cancel, but you're left because you have one side of the molecule that's nonpolar, because the carbon hydrogen bond's nonpolar, and then you have these two individual carbon chloride molecules. Those are pointed in a direction so that you have an overall net dipole moment for the entire molecule. So you have an overall net polarity. Okay, so in general, what are the rules of solubility for organic compounds? So the general rule is we have the like dissolves like rule. So if two substances or two different organic compounds have the same polarity, they will dissolve, or they're soluble. Okay, and if two organic compounds have opposite polarities, one is polar and the other is nonpolar, then they will be insoluble. Okay, so hydrocarbons, which are nonpolar, will not dissolve in water because water's polar. Only like dissolves like. Now, whereas if you have polar organic compounds, they're small, They contain a nitrogen or oxygen bond. They can dissolve in water because they form hydrogen bonds in water. So an example would be ethanol and water. So the ethanol, they both have, an ethanol has a hydroxyl group, and then the water, of course, has two hydroxyl groups in a sense, so that you can form hydrogen bonding between the ethanol molecules and the water molecules. Okay, so here's an example of solubility. Here's the condensed structure of hexane. It's a nonpolar molecule because it contains only carbon, it's a hydrocarbon, which are generally nonpolar. There's no oxygens or nitrogens, so it will not solubilize or not dissolve in water. And we know oil, this is like octane's like gasoline. This is similar to octane. We know that gasoline and water will not dissolve. Now, ethanol, of course, a small polar molecule with an oxygen that will dissolve in water. Okay, and here's an example of a molecule of cholesterol, and cholesterol is a very large molecule. But even though it contains a hydroxyl group, which is hydrophilic, or which I should say is polar, the rest of the molecule is so large that even though you have one hydroxyl group, which could form many potential bonds, there's too many of these nonpolar carbon-carbon and carbon-hydrogen bonds. So cholesterol itself is insoluble. All right. So we have let's round out this section, this introduction to organic chemistry with the focus on health and medicine. So we have certain vitamins, and then a lot of the properties of these vitamins depend upon their molecular structure and, of course, their organic compounds. Some of these molecules are either water soluble or soluble in water, and then some are insoluble. One of those is vitamin A, retinol, and it's important for our vision receptors. And here's the structure of vitamin A. We can point out some of the functional groups. There's definitely alternating carbon-carbon double bonds, and there's one hydroxyl group here. But generally, it contains many carbon-hydrogen, carbon-carbon bonds. So it's mostly a nonpolar molecule, and it makes this this is soluble because fats are nonpolar. The fats do not dissolve in water. So vitamin A is called a fat-soluble vitamin, so it can accumulate in fat tissue. Vitamin C, or ascorbic acid, is important for collagen formation, and the deficiency in vitamin C, of course, causes scurvy. So you get this vitamin C from fresh fruits, and here's the actual structure of vitamin C. So if we identify some of the functional groups, there's some hydroxyl groups, double bonds here, carbon-carbon double bonds, and then we have a keto group here, a carbonyl keto group here. So no, actually it's not a ketone because you have an oxygen next to it. So this would be representative of an ester, and then you have some hydroxyl groups here. So vitamin C, it has lots of these polar groups, functional groups on this, and you have a relatively small nonpolar, or you have many functional groups. You have many polar polar heteroatoms, but you only have a few of these carbon-hydrogen groups. So ascorbic acid tends to be water soluble, so this makes it a water-soluble vitamin. Okay, and the vitamin A and these other fat-soluble vitamins, these are readily stored in the liver and fatty tissues, whereas vitamin C, they're soluble in gastric juices and the blood. And these types of vitamins are excreted in the urine.